In the previous lesson, we redefined the primary trigonometric ratio using the unit circle. In this lesson, we are going to do some calculations. So first things first, let's review what we did in the previous unit, or previous lesson, sorry. Okay, the relationship between the point xy on a unit circle and theta. So cos theta is equal to x, sine theta is equal to y, and tan theta is y over x. Okay. So using the unit circle, try to answer the following questions. In which quadrants are the x-coordinates of the points on the unit circle positive? So you have an infinite number of points on the unit circle. Okay, but which of these points will have x-coordinates which are positive? So before we answer that question, just refresh your memory. You have 4 quadrants, and the way we label them is this is quadrant 1, and then you go counterclockwise. So this will be quadrant 2, quadrant 3, and quadrant 4. So in where are the points, or of all the points on this unit circle, where are the ones with x-coordinates that are positive? So hopefully you can see in quadrant 1 the x-coordinates are positive, and in quadrant 4. So 1 and let's say quadrant 1 and quadrant 4. And because we're talking about the x-coordinates here, we're going to say cosine theta is positive in quadrants 1 and 4. And of course, we're going to study the unit circle again and ask ourselves a very similar question. This time we're going to ask the y-coordinates, okay? In what coordinates are the in what quadrants are the y-coordinates of the points in unit circle positive? And if you study the circle, you'll get quadrant 1 and quadrant 2. So that means since sine theta is defined as the y-coordinate of the point on a unit circle, then sine theta is positive in quadrant 1 and 2. Okay, and then now we're going to look at the ratio of y to x for the coordinates. So y-coordinate to the x-coordinate, well, that is in quadrant 1 and quadrant 3. Wait a minute, quadrant 3? Yes, quadrant 3. Because if you're in quadrant 3, both the y-coordinate and the x-coordinate is negative because you go left and down. So if that's the case, negative, negative is positive. So in quadrant 1 and quadrant 3 is where the ratio of y to x is positive. And guess what? That means tan theta, because tan theta is defined as y over x, tan theta is positive in quadrants 1 and 3. So we're going to generate a rule to help us remember this. It's called the cast rule. So in quadrant 1, everyone is positive. When I say everyone, I mean sine, cosine, and tan. So we're going to put the letter A here in quadrant 1. In the second quadrant, the only trigonometric ratios which are positive are the sine ratios. In quadrant 3, it's the tangent ratios which are positive. And in quadrant 4, only cosine ratios are positive. So that's where we get the cast rule. So CAST, starting from the 4th quadrant and going counterclockwise. Now, if you are adamant on starting from the 1st quadrant and going counterclockwise, then there's this this saying to help you memorize it, which is all students take calculus. Most students prefer the cast rule, so that's what I will be saying for the rest of this unit. But if you like all students take calculus, you can do that too. All right, so we reviewed the unit circle and we introduced the cast rule. Now we know where the ratios are positive, or in which quadrants. Now we will look at another relationship between the trigonometric ratios using the unit circle. So I started off by writing out there are 2 points on the unit circle that will have the same x-coordinate, and there are 2 points on the unit circle that will have the same y-coordinate. And that makes sense based on the symmetry of a circle, but just in case you don't see that relationship, I've provided some diagrams here for you. Okay, so let's take a look at the first one. As shown in the figure to the right, there are 2 points on the unit circle with the x-coordinate of 0.6. Okay, so point A has an x-coordinate of 0.6, and point B has an x-coordinate of 0.6. Now, in order to reach point A, the principal angle is 53.1 degrees. Now, in order to reach point B, the principal angle is 306.9 degrees. Now, we said earlier that cos theta is equal to x, okay? So if that's the case, cosine 53.1 degrees and cosine 306.9 degrees are equal based on the diagram, and they are equal to 0.6, right? Now, I really want to highlight a relationship that exists between 306.9 degrees and 53.1 degrees. Now, you may already see the relationship, but just in case you don't, what I'm going to do is I'm going to find the acute angle between the terminal arm and the x-axis, which is called the reference angle. Remember, that was one of the terms that I really wanted you to remember from the previous lesson. So the reference angle here. What's the reference angle? Well, how do I find that? The whole circle is 60 degrees, so this is 306.9. So 360 minus 306. Hey, 53.1 degrees. Wow. You know what? I'm going to draw something else here. Those two triangles, those two right triangles, hopefully you can notice they are congruent. These are congruent right triangles. Okay, so I don't want to spoil it yet. I'll show you a few more examples, but we are basically trying to create these congruent triangles inside the unit circle. Okay. As shown in the figure to the right, there are 2 points on the unit circle with the y-coordinate of 0.8. So look at point A now, point B. They both have a y-coordinate of 0.8, which means sine of 53.1 degrees equals sine of 126.9 degrees, which both are equal to 0.8. Beautiful. Okay, so 126.9 degrees. Once again, guess what I'm going to do? I'm going to find the reference angle. Now, to find the reference angle of a quadrant 2 angle, you don't do 360 minus the principal. You do 180 degrees minus the principal angle. So in this case, it's 180 minus 126.9. It's basically finding the supplementary angle, which is, whoa, you guessed it, 53.1 degrees, which means this triangle here and this triangle here, these two right triangles are congruent. Now, if you imagine, if the triangles are not congruent, guess what? Let's go back to the previous diagram. If these two triangles were not congruent, guess what? These points won't line up as nicely as they do right here. Okay? And then you won't have this beautiful relationship. Okay, so you really want congruent triangles. If you want a y-coordinate of 0.8, you need this reference angle to be 53.1 degrees. All right, last one here, tan. Tan is y over x, so guess what? Tan of 53.1 degrees is equal to tan of 233.1 degrees. Now, be careful, negative is still positive. So negative 0.8 over negative 0.6 is the same as 0.8 over 0.6, which is 4/3. And guess what the reference angle of 233.1 degrees is? How do you find the reference angle? You take 233.1 degrees, the angle in the third quadrant, and subtract it by 180 degrees, which is, you guessed it, 53.1 degrees. Which means these triangles here, these right triangles here, they are congruent. and you want them to be congruent. Okay, if you want y over x to be equal, then you want the triangles to be congruent. Otherwise, you won't get that ratio. You won't get that ratio. You know what? Let's summarize it on the next piece of paper. So this is really important. In conclusion, any trigonometric function of an angle is numerically equal to the same function of its reference angle. The sign depends on which quadrant the original angle is located. So you know what? If that was too wordy for you, so sine 30 degrees, sine 150 degrees, sine 210, sine 330 degrees, they're all equal. Okay, numerically, the magnitude of the ratio. Okay, ignoring the sign, they're all equal 1/2. Okay. The ratios all have a value of 1/2 because the reference angle of 30 degrees, 150 degrees, 210 degrees, and 330 degrees is 30 degrees. Okay? Because the reference angle of 30, 150, 210, and 330 are all 30 degrees, if you can imagine, you're drawing those congruent triangles inside the circle in quadrant 1, 2, 3, and 4. Okay? The magnitude of the ratio is 1/2. The ratios all have, you know what? Instead of saying value, I meant to say absolute value, but you know what? I'm going to cross that. I'm going to say a magnitude, the size of the number. Forget the sign. So the ratios all have a magnitude of 1/2 because the reference angle, in this case, is all of them is 30 degrees. Okay, it doesn't matter. It doesn't have to be 30 as long as they're equal. Now, sine 30 and sine 150 are positive because sine is positive, or you know, it's okay. Sine is positive in quadrant 1 and quadrant 2. Sine is negative in quadrant 3 and quadrant 4. Remember, it makes perfect sense because sine is defined as the y-coordinate. Okay, y-coordinate of the point on a unit circle, so positive in quadrant 1 and 2, negative in 3 and 4. All right, let's do some math now. So sine theta equals 1/2. Sine theta equals 1/2, which means I either have a quadrant 1 answer or a quadrant 2 answer. Okay, so I'm going to draw it out. So quadrant 1, I won't bother drawing the circle, but I'll just draw the terminal arm shifting around. Or quadrant 2, okay? Because sine is positive in quadrant 1 or in quadrant 2. Now this here is our friend, the reference angle. So theta equals 180 degrees minus the reference angle. Well, what is the reference angle? This one I don't need a calculator because sine theta, a ratio of 1/2, that's an exact value which we can use to get our special angles. Hopefully you remember it's 30 degrees. So the quadrant 1 answer is 30, and the quadrant 2 answer is 180 minus 30 degrees, which is 150 degrees. And to check out the answer, sine 30, beautiful. Sine 150, beautiful. Okay, feeling good, feeling great about it. All right, next here. So where is cosine negative? Cosine is negative in quadrant 2 and 3. So we can draw it out. So draw the principal angle, draw the reference angle, alright, so what do we say here? Quadrant 3, this is the principal angle, this is the reference angle. So theta, if it's a second quadrant, we're looking at 180 degrees minus the reference angle. It's the third quadrant is 180 degrees plus the reference angle, right? Just based on your basic geometry. So the principal angle for the second quadrant, do I need my calculator? No. Root 2 over 2. That is the magnitude of the ratio. Root 2 over 2. Hey, that's one of our friends. It's one of our special angles again. This is going to give us a special angle. This ratio is going to give us a special angle of 45 degrees, right? Well, the reference angle is 45 degrees, which means the principal angle is 135 degrees and 225. You can check on your calculator, but I assure you they are correct. All right, moving on. So tan theta equals -3. I'm not going to draw the diagram, but it's either in quadrant 2 or quadrant 4. That's where tan is negative. So theta equals, so if it's quadrant 2, we're looking at 180 degrees minus the reference angle. If it's in quadrant 4, we're looking at 360 degrees minus the reference angle. Okay, now what's the reference angle? Unfortunately, I need my calculator for this. The magnitude of the ratio is 3. That's not a friend. That's not going to give me a special angle. So if that's the case, here's tan of 3, which means the reference angle is about 71.565, blah, blah, blah. So we're going to round that. So 180 minus the reference angle, that's going to give us our quadrant 2. Let's round it to 1 decimal place. So we'll do one more time. Inverse tan of 3, get the reference angle. Don't take inverse tan of -3. You can do that, but you're going to get a negative angle, and then you have to interpret that. So I always ask the students to find the reference angle. So just work with the positive ratio, find the reference angle, and then from there, find the principal angle. Because if you do -3, you'll get the negative angle, and you have to interpret that. That's a 71 degree, like let's say 71.6 degree rotation clockwise, which is actually identical to 288.4 degrees counterclockwise. Now, I can't write down -71.6 because there's a restriction here. I wrote theta has to be between 0 and 360. So I think it's best if we just solve for the reference angle by taking the magnitude of the ratio. All right, this one, sine is negative in 3 and 4. So quadrant 3 or in quadrant 4. You know, put the word or here. All right, so quadrant 3, we're looking at the principal angle is 180 degrees plus the reference angle. If you want, give yourself the diagram. For quadrant 4, it's 360 minus the reference angle. Okay, do I need my calculator? Definitely not. Root 3 over 2 is the magnitude of the ratio, which means using special angles, the reference angle is 60 degrees. And if you ever calculate on the test, you can most definitely check, but I assure you this is correct. Ooh, this looks fun. Sine 120, cos 300. Ooh, beautiful. I'm looking at all these. You know what? If it's not in the first quadrant, I'm going to find the reference angle. Okay, so 120 is not in the first quadrant. It's second quadrant, reference angle of 60. So it's going to be equal to sine 60 degrees because sine is positive in the second quadrant, right? So 300, hey, that's also positive because we're in the fourth quadrant. Cosine is positive in fourth quadrant, so this is identical to cos 60 degrees. Tan 135, now wait a minute, that's negative because 135 is negative. Oh, sorry, 135 is in the second quadrant where tan is negative. It's negative tan, and what's the reference angle? 45 degrees. So these are equivalent trigonometric expressions. Sine 120 degrees is identical to sine 60 degrees. Cos 300 degrees is identical to cos 60 degrees. Tan 135 degrees is identical to negative tan 45. So some students like this, they like to push it into the first quadrant, while other students, they just jump straight into the answer. Like they just figure out sine 120 like right off the bat. So it's up to you what you prefer. Sine 45 degrees, I'm going to leave that alone. Don't touch it. Cos 210, ooh, that's in the third quadrant, right? Third quadrant, reference angle 30. So this one is negative cos 30 degrees. because cosine is negative in the third quadrant. Tan 225, reference angle is 45. Should I add a negative? And the answer is no. I shouldn't add a negative because 225 is in the third quadrant where tan is positive. All right. So sine 60, you need to know your special angles. Root 3 over 2, 1/2, -1. So negative, negative, I'm just going to write the plus right there. So sine 45 is root 2 over 2. Cos 30 is root 3 over 2. And tan 45 is 1. So this gives me root 3 over 4 plus root 6 over 4, which is root 3 plus root 6 all over 4. Now, if I give this question a test, I'm definitely not letting you use a calculator because I don't know if it's your brain doing the work or the calculator doing the work. But since I do have a calculator right now, I'm going to quickly check. Sine 120, cos 300, tan 135 minus sine 45, cos 210, tan 225. So is this root 3 plus root 6 all over 4? Uh-oh, that is not good. Oh, it's because it's negative. Oh, I'm glad I checked. I'm glad I checked. Let me try to fix that one more time. Okay, let's see, negative root 3 plus root 6. There we go. You can check, but this, I remember the number. It's identical to what it was before. Ooh, close call. All right. Last part here, coterminal angles. These are very important later in the next unit, so keep this in your back pocket. What are coterminal angles? So coterminal angles are angles in standard position that have the terminal arm in the same position. Okay, so if you look at the angles 55 degrees, 415 degrees, and negative 305 degrees, as you can see in this diagram, their terminal arm or terminal side is in the exact same position. Okay, if the terminal arm is in the exact same position, then it makes perfect sense that sine 55 degrees and sine 415 and sine of negative 305 degrees is exactly the same, right? It's exactly the same. If the terminal arm is in the same position, isn't the x and y coordinate on the unit circle also going to be the same? So you can change sine to like cos or tan. All the ratios will be equivalent because the terminal arm is in the exact same position. Now, how do you find coterminal angles? Well, coterminal angles can be found by adding or subtracting by a multiple of 360. Because if you add by 360, you're just spinning around the circle one full revolution and back at the same spot. You can add by 720 and you just take 2 revolutions around the unit circle. Or you can subtract by 360. Now this way you're rotating clockwise as opposed to counterclockwise. So find 3 angles that are coterminal to 40 degrees. So what you can do is take 40 degrees plus 360, 40 degrees plus 720. Oh my goodness, they want 3 positives? Sure. And then plus 1080. So that will give me my 3 angles which are positive and coterminal to 40. And then take 40 degrees minus by 360 and 40 degrees minus by 720 degrees. That's negative 320 degrees, negative 680 degrees, and then 40 plus 360 is 400, 760, and 1120. Okay? Therefore, the angles coterminal degree are 400 degrees, 760 degrees, 1120 degrees, negative 320 degrees, and negative 680 degrees. Okay, Let me just quickly check. Yep. Beautiful. And just to bring the point home, for the example 1c, remember how I told you not to use a negative? I mean, you could use a negative, like inverse tan of -3. And if the calculator gives you -71.5, which is a 71-degree rotation clockwise, you can just find the angle coterminal to this. So add by 360. And bam, there you go. So there are a lot of different ways to do the question, but just try not to confuse yourself. Okay, so that was a very, very important lesson on reference angles and coterminal angles. Just remember to build those congruent triangles within your unit circle.